Good morning. I welcomes to all in our lecture series on quantum mechanics. Last class we have been discussed about bound and unbound states or regions. Actually, to discuss about particle in a finite square wave potential, that is also bound state, the basic idea about bound state and unbound states or regions. What are the so-called bound states or regions or unbound states or regions for the particle? The basic idea about this it is required. So only for that we discussed in detail about bound state and unbound states. So we taken the many examples, that is this is one example we have been considered potential step and rectangular potential barrier. We discussed that when E less than V0, that is total energy, this is total energy always this is this energy, this is the total energy always. Okay, total energy will be less than the potential of a region. If it is so, then which region will be the bound state or bound region for the particle, that we discussed for this case. And if E is greater than V0 for this rectangular potential barrier also we discussed and we discussed this one, this our present situation what we are going to be discuss. Okay, this one also we discussed in detail. Again we consider another problem, that is here you can see that potential and energy both are negative. Okay, both are negative, but here the energy, total energy is greater than that of the potential in this region. But if we are going to consider the potential is positive and the total energy E is positive, then what will be the scenario? Actually this is the sub case of our the so called infinite potential well, whatever we have been discussed in detail in our previous class. Okay, here I forgot a small things that I have to be tell to you, that that means if here energy is greater than that of the potential. Okay, here this depth is minus V0, right, and total energy is minus E, but here the total energy what is represented by the dotted line is greater than that of the V0. We have taken one example that is minus E is nothing but considered as minus 3, minus V0 is considered as minus 5. So here minus 3 is greater than that of the minus 5. But if this energy, this total energy of the particle, this is the particle, if the total energy of the particle if less than that the potential energy, then what will be the scenario? Okay, here you can see that for this case, see, in the region 1 potential is 0. Okay, in region 3 the potential is 0. Okay, in this region that is from minus A to plus A, what will be the potential? Potential is minus V0, right? And we consider that the total energy of the particle, this is the particle. Okay, the total energy of the particle is minus E, which is greater than that of the V0. Greater than that of the V0. If greater than that of the V0, then by according to the standard rule, minus E minus of minus V0 will be the positive value. Here we taken one example that minus E, that means minus 3, minus V0, that is minus 5. So here the total energy this value is greater than that of this value. So here if we are going to consider minus 3 minus 5, we got the plus 2 or here positive value for this case. Okay, so here positive means, carefully you have to listen, positive means in this region minus a to plus a, in the second region the particle is in the dynamic state, is in the motion state. This region is not the forbidden region, is not the forbidden, I am telling you, not the forbidden region, not the forbidden region. That means classically if this condition is given to us, that is here energy is greater than that of the potential energy in a region, in that region the particle is in motion state. Okay, but if we are going to consider region 1, here it is, you can see minus e minus 0 equal to negative, here also negative. Okay, so as we got that total energy minus potential of this region is negative in first region and second region. So first region, third region. So first region and third region is forbidden region for this particle. That means there is no dynamics, there is no motion in this two region, that is 1 and 3. Or you can say that this particle could not be penetrated to this region and this region. So this region is forbidden region for this particle, this region is forbidden region for this particle. The particle only can be move or in motion state or in dynamic state in this region 2. Okay, so in this way we can say that the particle is bounded in between these two regions 1 and 3. So the particle can be in dynamics in this region. Okay, now we are going to be consider the energy. This energy is negative but less than that of this potential. That means the energy what we are going to be consider, it will be here. Are you understood? What you got my point? Here if we are going to consider the energy value is here, that means this energy is greater than that of the this potential. But if we are going to consider the energy is here this total energy is negative, this total energy is negative. Here if we are going to consider this total energy is negative, but this total energy is less than that of this V0. Okay, so if you are going to be consider this depth from x is equal to 0 to this depth will be, suppose you can take this minus e. So here we consider minus v0 means minus 5. Okay, this depth we considered with an example minus 5. So if we are going to consider the total energy will be at here, the total energy will be at here, that means below this potential. That means we have to consider that minus e will be nothing but minus 7, because minus 7 is the less than that of the minus 5. Okay, so now you can see here we are going to be subtract the total energy minus potential for this region and this region and this region. First region 2, you just see for region 2 total energy is how much? Minus 7. We consider with an example minus 7 minus the potential is how much? Minus 5. Minus of minus 5 is minus 2. Here we got the negative. For region 2 we got the negative value, right? For region 1 you consider region 1 obviously it is minus 7, minus 0 is minus 7 is negative also. Minus 7 means negative, and region 3 also same, minus 7 we can get is negative. That means whenever we are going to be consider the energy is negative and less than that of the potential, then in that region the particle is not going to be motion anymore. That region will be the forbidden region. Okay, so here if we are going to be consider minus E of is the total energy of the particle in this region 2, then that particle, suppose initially it will be here, it will remain at here, it could not be moved, because we found total energy minus potential energy is the negative value. Okay, so that means in the region 2 itself the particle could not be moved. It is classically forbidden region. It is you can say it is bound region or restricted region for the particle for motion. And region 3 and region 1 and 3 also the forbidden region. So in this way, if we are going to take the energy is negative and also less than the potential, that is your forbidden region. So overall I can say that here these things also I discussed in the last video, that E minus V0, that is total energy minus potential. If positive, this is unbounded state or scattering state. If it is negative, then it will be bound state. Okay, or bound region or forbidden region of the particle. That means in that region the particle don't have any motion. Now come to the main topic of our syllabus, that is particle in a finite square well potential, that is the so called bound states. Bound state, not the states, bound state, because this is only is bound states. States no problem that much, because here two regions is restricted regions. So due to two regions, this particle is in bound state. This is it is only moving in this region. So you can say bound states. Bound states means here it is bounded. This is also bounded. Okay. So now here I pasted one write up, because initially I written this one. So I just modified these things. May you can found in your last video, whenever I am discussing about bound state and unbound states, that means last video you can found this write up. I just modified somewhat this write up, this much only this much I have been modified and written like this. You have to write this one. Okay, and there is no modification in this figure. So what I written, I'm just reading, you just watch. Already we discussed. Okay, so now we are going to start this topic with step by step or with line by line, you can say. So here I written that according to classical mechanics, if total energy of a particle, you can write E, that may be positive or that may be negative. You can write E over here. Okay, you can write E, total energy of a particle minus potential, you can write Vx, V function of x. That means we are discussing the one dimensional only. Okay, if total energy of a particle in bracket E minus potential, that is Vx, V function of x, that means one dimensional along x axis of a region, potential of a region, total energy of a particle minus potential of a region is equal to negative value. That means that is less than 0. That is less than 0. This is written as that is I dot E. I dot E. That is less than 0. Then that region will be the forbidden for that particle. We discussed in detail. Okay. Or particle remain confined in that region. Okay. Or there is no classical motion would be possible in the region. GION, region. That means I told that suppose just now I discussed that in this region if we are going to consider this total energy is less than that of the potential energy, we can found the total energy minus potential energy will be negative. That means the particle is confined in this region. Suppose particle will be in this region, it could not be moved anymore in this region. So only for that I written particle remain confined. If it will be there, initially it will be there. There will be no motion in this region. Okay. And if it is motion in this region and this is in this region and this region we got the negative value, it could not be penetrate. That is our classical model. And also we can say that there is no classical motion would be possible in the region. Okay. So in any region, if total energy of the particle minus potential of a region will be negative or less than 0, then that region will be called as the forbidden region, or particle remain confined in the region, in that region, or there is no classical motion would be possible in the region. What we discussed with our examples last video and the beginning of this video. I told that if we are going to consider this total energy which is negative and also less than that of this. So if the particle will be remain here, initially it will be here, also it will remain here, means confined in this region. There is no motion classically. Okay. So this is our ideal square wave potential, where this particle is confined due to region 1 and region 3. Due to region 1 potential and region 3 potential, this particle I have been marked as a star and having the mass is m. The mass of the particle is small m. Okay. Small m, and it is confined due to this is region 1 and 3. How it is we are going to be discussed. You just I am going to explain what I drawn in this figure. See, at x is equal to minus a and this onwards, means up to minus infinity, the potential is 0. X is equal to minus a and plus a, the potential is minus v0 here. And beyond the x is equal to plus a up to plus infinity towards this side is Vx is equal to 0. Okay, and we consider the energy is this much, total energy of the particle which is inside this region 2, initially. This is our particle which is inside this region 2 having the total energy is this much, which is higher than this potential minus V0, that is considered as minus E. Okay, so the same thing whatever in the figure I have been written here. See, let consider a particle of mass m and total energy E, that is negative, in bracket I have been written negative, is confined in a finite potential well defined as shown in the figure, and that potential well defined as that is Vx equal to 0 for x less than minus 1 is considered as region 1, equal to minus V0 for minus a to plus a range, that is considered as region 2, and equal to 0 for x is greater than 0, that is your region 3. Okay, so the quantum mechanical result shows that there are discrete energy values in the well and wave function is non-zero. It is interesting. Two things here we are going to be found: discrete energy value and wave function is non-zero, means not zero, in the classical forbidden region 1 and 2, where E is less than 0. This will be verified by this discussion, with this discussion. That means what it is told, that according to quantum mechanics, see, according to classical mechanics, already we discussed that as this is this mass m having the particle having the total energy minus v, and the potential is minus v0, and this is minus e is greater than that of the minus v0. So this particle can be moved in this region, but it could not be penetrate this region and this region, classically forbidden regions. For this particle, region 1 and region 3 are the classical forbidden regions for this particle, already we discussed. But quantum mechanically we can get the results, or it is written that the quantum mechanical result shows that quantum mechanical, what we are going to found, that there are discrete energy values. Suppose this first two things we are going to be found. This particle is confined, means the energy will be not continuous in this region, energy will be discrete. That this type of things already we got whenever we have been discussed the infinite potential well. In case of infinite potential well, may you remember that in case of one dimensional infinite potential well, suppose the particle will be here, Vx is 0 here, and beyond this is infinite and infinite potential, the energy will be discrete value. Okay, energy will be discrete value. So here also, whenever the bound particle we are going to be get in the bound state, in this bound state we are going to get the discrete energy values and non-zero wave function non-zero. If wave function non-zero, then that implies probability density also non-zero. Okay, if wave function non-zero, probability density also non-zero. So wave function is non-zero in the classical forbidden regions. Classical forbidden regions, that is in region 1 and 2. Region 1, that is in region 1 and 2. That means in quantum mechanical we are going to be found that in this region 1 and region 3 also there is some wave function exist. Also there is some probability of finding the particle will be exist in this region and in this region. But it will be like this. It will be like this and it will be like this. It will decrease with increase of distance. That means I can show you that scenario here. In the region 2, this is your region 1, this is your region 2, and this is region 3. That means in region 2 it will be in dynamic state. That means we can consider in the wave form or oscillatory form. But in region 3 and region 1, classically it is not acceptable. Classically we are not going to be found the particles. This is the, suppose the star is the particle dynamics. The particle dynamics or presence of particle in the region 1 and 3 not to be acceptable according to classical point of view. But according to quantum point of view, also we can found wave function of this particle in this region and this region also, but it is decreases. The wave function is going to be decrease, or the probability density is going to be decreases with increase of distance from this point and from this point also. That we are going to be found whenever we are going to be discuss the behavior of the particle followed by the Schrodinger equation. Okay, so first we have to consider the time independent Schrodinger equation. TISC is nothing but our time independent Schrodinger equation for all the three regions. Then we can easily found the dynamics of the particle in this region and this region. in these three regions. So first we have to consider the Schrodinger equations in these three regions. Okay. So before we have to write down the time independent Schrodinger equation for all the three regions, first we have to just define what we have. We have the total energy, that is E, is less than 0. That is, total energy is equal to minus E, considered as negative. It is negative. Already we have we are taken that negative value, right? Now the general form of time independent Schrodinger equation is, in our general form, is d square psi. It is one dimensional. Okay, in general the one dimensional 1D time independent Schrodinger equation is, what is that? That is d square psi by dx square plus 2m by h cross square E minus Vx psi equal to 0. Let it is equation number 1. Here E is the total energy of the particle, m is the mass, and Vx is the potential of the region. Okay. Now we have to consider the first region, region 1, and we are going to set the time independent Schrodinger equation for region 1. The region 1, in the region 1 we have E, total energy is nothing but minus E, right? And Vx, the potential of that region, is 0. Now we have to just put the value in this equation number 1. Hence TISE will be, by equation number 1, by considering equation number 1, by equation number 1 or by considering equation number 1, just instead of psi we are going to be consider psi 1 for region 1. Okay, d square psi 1 by dx square plus 2m by h cross square. Instead of E we have to write minus E minus potential is how much? 0, psi 1 equal to 0. That implies d square psi 1 by dx square minus 2m by h cross square E psi 1 equal to 0, right? Let k square equal to 2m E by h cross square. So that implies this equation will be d square psi 1 by dx square minus k square psi 1 equal to 0. Let it is equation number 2. Now we have to consider the region 2 and its corresponding time independent Schrodinger equation. Hence time here now for region 2, the heading is now for region 2. Region 2 is nothing but the total energy is minus E, and Vx is nothing but how much? Minus V0. Minus, this is minus, okay, minus V0. We have to check the figure. See, this is our region 2. In this region the energy is that one, that much only, minus E, but the potential is minus V0. That we are going to be put in our equation number 1, or in the general time independent Schrodinger equation we can found the time independent Schrodinger equation for region 2. So if we are going to put E equal to minus E, Vx equal to minus V0 in equation number 1, what we can found? We can found that d square psi 2, here psi 2 is considered as wave function in the region 2. Okay, so d square psi 2 by dx square plus 2m by h cross square. Instead of E, see here, instead of E we have to put minus E, instead of Vx we have to put minus V0, minus E minus V0, psi 2 equal to 0 by considering equation number 1. So d square psi 2 by dx square plus 2m by h cross square, this will be plus, minus will be plus, this is minus, so V0 minus E psi 2 will be equal to 0. Let beta square equal to 2m by h cross square V0 minus E, this much is considered as beta square. So hence this equation will be d square psi 2 by dx square plus beta square psi 2 will be equal to 0. Let it is equation number 3. Similarly for region 3 we can write the time independent Schrodinger equation. See, for region 3, that means E equal to minus E, Vx equal to 0, Hence, using equation number 1, time independent Schrodinger equation, TISC, time independent Schrodinger equation for region 3 will be d square psi 3 by dx square. Here psi 3 is considered as the wave function of the particle in the region 3, plus 2m by h cross square minus e minus vx is 0, psi 3 will be equal to 0 into psi 3 equal to 0, d square psi 3 by dx square minus 2m by h cross square e psi 3 equal to 0, considered k square equal to 2m e by h cross square. So hence this equation will be d square psi 3 by dx square minus k square psi 3 will be equal to 0. Let this equation number is 4. Okay. Now the general solutions of the second order differential equations, that is 2, 3 and 4 will be, see these equations, that is equation number 2 for region 1, equation number 3 for region 2, equation number 4 for region 3. These all are the second order differential equation, and we can find the solution easily because already many times we have been interacted this type of second order differential equation, and we can write directly here psi 1 wave function, psi 1 or the solution of the equation number 2. Here I am going to show you for solution of equation number 2. For finding the solution of equation number 2, we are going to find out the auxiliary equation, right? So here the auxiliary equation for equation number 2 is nothing but your, see, this will be m square minus k square is equal to 0. So m is equal to plus or minus k real. So solution psi 1 I can write some constant. Here I written some constant a e to the power kx plus b to the minus kx. Okay. Now we have to consider first this is psi 1 and psi 3, then psi 2 we are going to consider. Psi 3, see psi 3 also same, m square auxiliary equation. So m square minus k square will be equal to 0. So psi 3 also it will be in the form of f e to the power kx plus g e to the minus kx. Now psi 2. Now we have to consider the for region 2 what will be the solution. See, in case of region 2 the equation is this one. So this the auxiliary equation will be how much? Auxiliary equation will be m square plus beta square is equal to 0. Okay, so m equal to plus or minus I beta. Okay, so as it is two roots, so the two solutions can be acceptable. Let it will be s e to the power I beta x plus t e to the minus I beta x. So general solution, so two solution will be acceptable, this one and another you can consider this will be the y2. So general solution will be the addition of these two solutions. So that will be your psi 2 will be equal to s e to the I beta x plus t e to the minus I beta x. This type of things we done many times. Okay, so this is our general solution for the equation number 3 or for the region 2. So this also can be written in the form of sine and cosine. See s into this will be cos beta x plus I sine beta x plus t into cos beta x minus I sine beta x. Okay, so here you can see psi 2 will be equal to s cos beta x t cos beta x. So s plus t cos beta x. So here I sine beta x here minus t I sine beta x. So it will be written as sine beta x into is minus it. Okay, so s plus t can be considered as c suppose, and is minus it can be considered as d. So psi 2 can be written in the form of cosine and sine. It will be cos beta x plus d sine beta x. This type of things we have been done many times in our quantum mechanics. So the solution of the equation number 3 or the wave function in the region 2 is in the form of cos and sine. That means it is oscillatory. Here also it can be identifiable because it is in the form of the imaginary, so it will be oscillatory. But so here see, same thing I have been written over here. C cos beta x plus d sin beta x, let it is equation number 6, and psi 1 we found in the form of a e to the power kx plus b e to the minus kx, and psi 3 we found f e to the kx plus g e to the minus ikx. Okay, psi 3, psi 2 this one. So from this above solutions, which is represented by the equations 5, 6 and 7, it can be perceived that psi 1 is not oscillatory. It is increasing exponentially, decreasing exponentially term is there. Okay, psi 3 also exponentially increases and exponential decreases term is there. Okay, psi 1 and psi 3 there is not oscillatory, but psi 2 is oscillatory because it is in the form of cosine and sine form. So we can say that for the classical point of view, we can say that this region and this region is forbidden for this particle. But however, quantum mechanically we found there is some wave function possible. Wave function is not zero here. Here wave function is not zero means the existence of the particle in the region 1 can be expected and 3 also expected, because wave function we found finite. The wave function psi 1 is there, psi 3 also exists. So the particle can be penetrate. We can imagine, or we can say the particle can be penetrate in the classical forbidden region 1 and 3. Okay, so this is interesting. So 5, 6, 7 is the solutions or wave functions, or you can say the dynamics or the behavior of the particle in region 1, 2 and 3. We know that for well behaved acceptable solution, the wave function should be obey the boundary condition as psi x tends to 0, x tends to plus or minus infinity. So we can get the wave function in any format, but it has to be obey the boundary condition, it has to be normalized, then it will be acceptable. So if we are going to consider all the 3 wave functions in the region 1, 2, 3, is it well behaved? Then if it is well behaved, then it has to be obey this boundary condition, that is psi x should have to be 0 when x tends to plus or minus infinity. Means here is the particle, we have particle is here, its probability in this state for this problem, the probability of finding the particle at exactly this position will be maximum. So probability of finding the particle beyond this side and this side, it will be decrease. So and here it is restricted region. Quantum mechanically we can get some particle behavior here, some particle behavior here, but someone is going to tell that particle also exists at the minus in plus infinity. Is it going to be acceptable? Is it acceptable? Not acceptable. Somebody is going to be say that the particle existence will be at minus infinity. At the minus infinity also particle will be exist. For this problem, is it going to be acceptable? Is it not acceptable? So at minus infinity and plus infinity, the particle could not be exist. If we are going to consider a particular problem, particle will be here. The particle could not be exist at plus infinity and minus infinity. That means particle behavior at plus and minus infinity will be 0. That means psi x will be 0 here at plus infinity, at also psi x will be 0 at minus infinity. This is one of the boundary condition in our quantum mechanics. So so psi x will be tends to 0 when x tends to plus or minus infinity. Now we are going to be consider b to the minus kx, which is the one of the part of the wave function of the region 1. Okay, of the region 1 region means this one, means x minus here minus a, so this side minus is going to be increased. So suppose it is minus 2, minus 3, minus 5 up to minus infinity, like that it is going to be increased. Okay, so here you can see that this term b to the power minus kx, so x is going to be minus minus, it is going to be increased. So initially it is minus 2, then minus 3, then minus 4, then minus 5, like that. If it will minus 2, it will be plus kx, minus 3 minus 3x, minus 5 minus 5x. That means if x is going to be increased minus infinity up to minus infinity, this is minus infinity, minus is there. Okay, minus infinity, I am going to be write once again, it is not clearly identify. Minus infinity, you can see minus 2, I am going to put, it will be e to the power 2x, sorry 2k, 2 minus 2 minus is there 2k, then 3k, then 5k. That means if we are going to move towards minus infinity, this value is going to be infinite, it is increasing, this value is increasing. Like that, if we are going to consider this term of this solution, this one, that means this is the wave function of the region 3. See, wave function in region 3 means x value is going to be increased with positive 2, 3, 4, like this. So you can put, if we are going to be consider this term, and we are going to put 2, it will be 2k, 3 it will be 3k, 4 it will be 4k, 5k, and that means this will be going to be infinite when x tends to plus infinite. This is plus is there. Okay, plus infinite. So this and this is not going to be acceptable, this term and this term, this function, this two function is not going to be acceptable if we are going to be consider this boundary condition. Okay, so for the region 1, this term is not going to be acceptable, for the region 3 this term is not going to be acceptable. So hence b e to the minus kx, f e to the kx is not well behaved or not to be accepted. So it is not going to be accepted for the solution of the region 1 and region 3. So this is going to be not going to be considered, this one and this one. So finally the solutions of the region 1, 2 and 3 are, hence the final and acceptable solutions for the three regions are psi 1 a e to the kx, because b e to the minus kx is not going to be considered. Likewise in psi 3, f e to the kx is not going to be considered, we are going to get g e to the minus kx, and psi 2 is same c cos beta x plus d sin beta x. Let this is equation number 8, 9, 10 respectively. And we know that these are the so called your coefficients, and these coefficients a, c, d, g, a, c, d, g can be calculated by using boundary conditions. For this case the boundary conditions are a, psi 1 at x is equal to minus a will be equal to psi 2 at x is equal to minus a. So minus a and plus a are the two boundaries. See, here this is one boundary, this is one boundary. Boundary means it is separating two regions. This boundary at x is equal to minus a, it is separating region 1 and region 2. This at x is equal to plus a, it is separating region 2 and region 3. So at this boundary, this wave function exactly at this boundary, this wave function and this wave function will be equal, and it is also continuous. Means first derivative and first derivative of this wave function and first derivative of this wave function is going to be equal at exactly at minus a. First, here we confirmed that there is the existence of the wave function in region 1, 2 and 3, and boundary condition is tells that exactly at x is equal to minus a, this wave function will be equal to this wave function, and both are continuous at this boundary, at this interface. Otherwise how we are going to say that the particle from this region is moved to this region? Okay, so it is moved to this region means it has to move through this boundary. So the particle is moving from this to this region, means here at this exactly this position both are equal, and the first derivative, continuous means first derivative, slowly, first derivative means slowly it is changes its slope at this boundary. First derivative and first derivative of this and this is going to be same. Similarly, the wave function at x is equal to a for this region, that means 2 and 3 will be equal, and the first derivative means the wave function it changes from here to this region, means at exactly this point this is slowly, smoothly it is changes its behavior from this to this. So first derivative of psi 2 will be equal to first derivative of psi 3 at x is equal to a, and also both are equal, psi 2 at x is equal to a, psi 3 at x is equal to a. These are the 4 boundary conditions I have been written over here. Psi 1 at x is equal to minus a, psi 2 at x is equal to minus a. First derivative, that means slope, or you can say the continuity, or it can be also called as the gradient. Okay, gradient of psi 1 at x is equal to minus a, psi 2 gradient or continuity at x is equal to minus a, both are same. Okay, and similarly psi 2 at x is equal to a, psi 3 at x is equal to a will be the third boundary condition. Psi 2 d psi 2 by dx at x is equal to a, and the first derivative of psi 3 d psi 3 by dx at x is equal to a, both are continuous. Here it is the one pictorial dynamics or representation of the given problem what we are discussing here. That means particle will be here, and in this region, this is our region 1, this is our region 2, this is region 3. In this region the particle is in the oscillatory motion, and suppose we can consider that this is our incident radiation. Suppose particle starts from here and incidents over this boundary, and this will be its reflected one. So incident energy with a greater amplitude and frequency, reflected will be amplitude will be reduced and wavelength will be increased. In this way we can represent, and exactly at point this, see, exactly at this point can you identify this one and this one, means the psi 1 and psi 2 both are equal at x is equal to minus a, and here this is psi 2, also psi 2 and psi 3 both are equal at x is equal to plus a. Okay, and also the slope exactly at this point you could not identify the slope at x is equal to minus a will be for this one or this one. That means the slope, that means dx1 by dx, d psi 1 by dx at x is equal to minus a is equal to d psi 2 by dx at x is equal to minus a, which is our second boundary condition. Similarly, the slope at this point at x is equal to a, that is your d psi 2 by dx at x is equal to a, d psi 3 by dx at x is equal to a psi 3, that is your fourth boundary condition will be satisfied at x is equal to a. So this is the pictorial representation of the dynamics, quantum mechanical dynamics, but classically this is not possible. Classically the particle will be here only. Okay, quantum mechanically some probability is there, some probability is there. So next we have to discuss now, considering boundary condition, how we are going to be find out a b sorry a c d g, that we are going to discuss in the next page. Actually I am thinking that here we have to be stopped, because already the video is more than 50 minutes. So here it is going to be start how to consider the boundary conditions and finding the a c d g values. These are too long also, so I am thinking that we have to be discussed in the next video. So we have to be stop over here. That means in this video we have been discussed up to this boundary conditions and this figure. Okay, this is figure 2, and this up to this much we have been discussed, and we have to be stop over here. In the next class we are going to be discuss, or the next video or next part of this topic we are going to be start from here. Okay, so Thank you so much for watching this video. And in the last class itself I told that you have to write down the note regarding bound and unbound state or regions, because this topic is not exactly in your syllabus, but I given basic idea about this one bound and unbound states in that last video. And this video also I discussed if this if this energy is negative and less than that the V0, how it will be bound state, or this region how it will be bound state I also explained. You can add this one also, this case, in your note. Whatever I told, that you have to write down the note for the bound and unbound states. Okay, and you have to write down the notes for this topic that is your this much. And I explained each and every word itself, all the things of this note. That means up to first page, second page, third page, up to fourth page we have been discussed in detail. You have to write down your note, complete it perfectly, and be ready for the next class. That we have to start from here. That is, consider boundary condition A and B for equation number 8 and 9. We get this one. Okay, so thank you so much for watching this video. Thank you.